All right, while it's recording, so your R of t is t cubed t to the 4th.
There we go, I got it.
You got it? Oh, good.
I
Okay.
I changed my values for A and B. I changed the top one, but forgot to change
The bottom one. Okay. All right. So we have here the integral from 1 to 2, although your numbers might be different. So x over y, you have to convert to t. So you have t cubed over t to the 4th, and then you multiply by the square root of x prime squared plus y prime squared. So you have 3t squared squared plus 4t cubed squared dt. How do we do with our initial setup? Everyone okay? Okay. So integral 1 to 2 of 1 over t square root of, so this would be 9t to the 4th plus 16t to the 6th. So I would definitely pull a t to the 4th out of the root. So if you pull a t to the 4th out, it ends up becoming a t squared. So you have a t squared over t times the square root of 9 plus 16t squared. And then now you can do a u sum. All right. So your u, 9 plus 16t squared, du, 32t dt, so we have to divide by 32. Is that okay? I heard a groan. You all right? Okay. So I'm going to rewrite. I'm going to go ahead and just convert to u's. So t is 1, u is 25, and then 64 plus 9 is 73. Am I right?
Oh, I have different numbers.
Oh, okay.
I have 1 and 4, you have 1 and 2.
Okay.
I have that too.
Okay. Oh,
But you're
okay.
converting to you.
Well, why not? Right?
Oh,
So 1/32 root u du. So this is u to the 1/2. So 2/3. So 1 over 3 times 16. 1 over 48. U to the 3/2 from 25 to 73. What crazy numbers. All right. So we have 1 over 48. I'm not simplifying. 73 to the 3/2 minus 125. That's what I got. Okay. Did you get that?
Yeah.
Okay.
That's what I got too.
Is it?
Oh, I mean, I got the answer.
Oh, good. Okay.
Some of the things I tried doing like the plug-in U, like plug in like the fourth, like the one, like the 2,
Uh-huh.
and I got the wrong answer.
Oh.
You must.
Things that always happens. I always get wrong. I kind of way, so I never do it.
So you just convert back.
Yeah.
There's some I got.
That's fine.
25 and 2.
All right. Any other questions about just a basic standard line integral? We're all comfortable with a basic line integral.
How about like when like you're not given the X's and Y's and the T's, or like the
Where you have to come up with your own parametric function?
Yeah.
I'm going to table that until we get through this, and then we'll do some coming up. I want to look at your test and see if I can make you do that.
Okay.
That might help.
Oh, that'd be so great.
Okay. All right, number 3. So take a look at your number 3. My number 3. I think the only thing that's different is the exponents on the t's. So evaluate the line integral f dot dr where c is given by the vector function r of t. So first thing I would check for is f conservative, but it doesn't look like it's conservative. So you might have to go ahead and just do f dot dr. and that's okay. So see if you can find your dr and then write up your integral with f.dr. For the recording's sake, everyone in class got this one right without any help, so we're skipping it and going on to the next one. All right, where's my next slide button? There we go. All right, so number 4. Show that the line integral is independent of path by finding a function f such that the gradient of f is equal to big F. So what are you actually finding? You're finding the potential function, right? Yes. All right. So go ahead and find the potential function. Once you find the potential function, if the potential function exists, and I'm pretty darn sure that it does. Yeah, so it does. Then you can evaluate the integral. There are multiple ways, but one way is the easiest, right? All right, so when you integrate, I'm going to call, I don't know what to call it. So why is it not working? Something's up with my board. Let me see if it's working now. I just tapped it. There we go. Okay. So, when you integrate f like dx, I don't know how to say this, like the x component I never know how to write that. Anyway, the x component dx. It's not. This is bad notation. But anyway, so you have x squared e to the negative y, right? So I'm not going to write that. I'm just going to put x with a colon. So your x component is x squared e to the y. Then your y component is y squared plus x squared e to the negative y, right? And it's just, that's it. It's just an x and a y. So your f of xy would be y squared plus x squared e to the negative y. Do they make you do like a plus k on here? No? So should I not take off if you don't have a plus k on here? All right. So when you evaluate the integral, I personally would use fundamental theorem of line integrals, which says that that integral is equal to your potential function evaluated from the beginning point to the ending point, right? So you just plug in the 5, 1, and then minus plug in the 1, 0. So 1 plus 25 over e minus 0 plus 1. Oh, that's e to the, let's see. Yeah, e to the 0, so it's just plus 1. X is 0, x is 1, y is 0, yeah, plus 1. So I just get 25 over e. If I did my math right. Okay. All right. Any questions on finding a potential function or evaluating a line integral using fundamental theorem of line integrals? Everyone's okay with all that? Moving on. All right. Consider f and c below. F is that vector function. C is the arc of the parabola y equals 4x squared from that point to that point. This is the same kind of thing. You're finding a potential function and then plugging in your points. So do you guys want to do this real quick?
Yeah.
I mean, okay, take a minute, you do it. I'm not going to do the whole thing, but your potential function for this, it's just one. Come on. Don't give me issues today. 1/3 x cubed plus 1/3 y cubed plus k. Although they don't use a plus k. All right. So anyway, so since this is a conservative vector field, you can just say that this equals, and you go from start to finish. So your start is down here. Your ending is up here. doesn't go low to high, it goes start to finish, right? Start on the bottom, ending on the top. Good. Can you all take it from there?
No.
Yes.
I mean, I can't understand my answer.
All right, I'll take a closer look once I move on to the next problem. I'll go back and take a look at your answer. Okay. All right, next one. A particle starts at the point -4, 0, moves along the x-axis to 4, 0, then along the semicircle, y equals the square root of 16 minus x squared to the starting point, which means we have a simple closed region, right? So use Green's theorem. They're telling you to use Green's theorem. I might not tell you. I might just expect you to notice it's a simple closed region and on a non-conservative vector field, and therefore you can use Green's theorem, right? So anyway, so use Green's theorem to find the work done on this particle by the force field 3x x cubed plus 3xy squared. So remember, this is the one where you kind of go opposite. Remember, Green's theorem is very similar to the test for conservative, where you do dn dx minus dm dy, right? That's your integrand. And you're integrating over the area of the bounded region. All right. I think it'll let me write right now. All right. So we have, I'm going to try this region. 4, 4. Go that way and go that way. Okay. So let's see. dn dx. We have 3x squared plus 3y squared minus 0. Dx. Y goes from 0 to the root of 16 minus x squared. X goes from -4 to 4. Okay. Yeah, this is just screaming out for polar, right? Yeah. Okay. So polar, I would go 0 to pi, and my radius would be from 0 to 4, and so then I'd have, this would be 3r squared, but I'd have to multiply by another r. ERD theta. Did you guys get that for your setup? With maybe different numbers depending?
Yes.
Okay. All right. Okay, so I'm going to think of this as 3r cubed, so I'm going to have 3 fourths r to the 4th, from 0 to 4, d theta. So 0 to pi, so 4, 64. What's 64 times 3? 3 times 64. I'm just going to write it. Theta. What's that? 180. 192? 192. So I end up with 192 thetas from 0 to pi. I get 192 pi. You guys probably got something different if your numbers are different. But the setup probably will be similar. Makes you like polar, right? Aren't you liking polar now more and more?
Yeah.
It's polar. I still despise.
Whoa. Despise spherical. Okay. Wow. That is, the word loathe was used today at lunch by Mr. Kingsbury about Alvin and the Chipmunks. So, yes.
You guys are very
He didn't know. He just doesn't like them in general. It was funny.
It's like a 1960s classic.
Yep. All right, any questions on this one?
Yeah.
Are we good? Danny, how you doing? Tijesh, you have a question?
What's the why is it 0 to pi not 0? Oh, wait. No.
Because you're only doing the semicircle, not the whole thing. Is that okay?
Yeah.
Good. Any other questions? No? We're good? Colin, you good? Nick, how you doing? Yeah? Okay. All right, moving on. All right, number 7. Determine whether or not the vector field is conservative. If it is, this is another potential function question. You don't even have to do anything else. Like, super easy. Well, kind of. So, it's really not bad. So, take a minute, see if you can find the potential function for big F. All right, to save time, and because we're going to find the curl later, I'm not going to find the curl right now. So, you know what? I liked that someone was doing, like, showing it like this. I think that was Dorsa who was doing it like this. So, show this y cosine z d. All right, so this we get x. This we get y sine z. And then this one, hey, we get y sine z. Okay, so for my potential function, I get x plus y sine z plus k, even though they're not going to do a plus k.
Yeah.
All right, did you all get something similar? Good. Let's move on. Whoa, that's a big one. Okay, this is just finding curl and divergence. Pretty straightforward. So curl, remember, is the cross product of the gradient symbol and your vector, and divergence is the dot product of the gradient symbol and your vector. Have you guys already done this? Am I like way behind you? No? Okay, so take a minute, see if you can find the curl and divergence. Just kind of pay attention, follow along. So curl. Do partial x, partial y, partial z, and you have 9xy e to the z. There is no j, and then y z e to the x. All right, so I get z, let's see, z e to the x minus 0 for my first, and then for my middle, I get y z e to the x minus, oh, and this is negative, plus dz 9xy e to the z, and then the last one would be 0 minus 9x e to the z. All right, that's kind of confusing. All right, did you get something similar to that for your curl? Okay, and then your divergence. So divergence is actually, I'm going to just do it up here. So it's your partials dot product with your vector. 9xy e to the z and 0 comma y z e to the x. Okay. So your divergence is 9y e to the z plus 0 plus y e to the x. That's what I get from my divergence. How'd you do, Nathan? You got it? Good. Any questions on curl or divergence? Just finding them. Everyone okay? In the back? Ian, you good? Yes? Okay. Vikram? Okay. All right. Okay, finding a parametric representation for a surface. It says let x, y, and z be in terms of u and or v. Honestly, just let one be u, let one be v, and then solve for the remaining variable in terms of the other two. Like, you really, there's nothing, you don't have to make it any harder than that. So, and you honestly, you just pick a letter. So, What do you want x to be?
U.
X is u. All right. What do you want y to be? Y is v. Then z, if you solve for z, z would be, let's see, lies in, oh, wait, no, okay. Lies in front of the yz plane. So personally, I would let y be u, z be v, and then that way you can do a positive root for x and have it be in front of the yz plane without any major restrictions. Right?
Yeah, then it's y to y.
Yeah.
Wait, why does it matter which one's U and which one's V?
It's
Because it's got to be in front of the yz plane. So that means you're going to want to solve for x in terms of y and z, not the other ones around. So here, just watch. If your y is u and your z is v, so then if you solve for x, right, you would normally you'd get x squared equals 4 minus plus 4y squared plus z squared over 4. Whoops, and then x would be the square root of that, normally plus or minus, right? Except this is the part that's in front of the yz plane, which means these are only the positive x's, so it's just the positive square root. So you can just let x be the positive square root of 1 plus y squared plus z squared over 4. And then you've covered the whole thing without having to worry about any, like, if you let this be u and this be v, how are you going to write z so that it's in front of the yz plane?
Oh, okay. And then
Right?
you would change the Y and the Z to use the V's, right?
Yeah. Oh, sorry. This should be u and this should be v.
Oh, yeah.
I'll just erase it. One plus u squared plus v squared over 4. There we go. So that is actually even harder than the one on your test, right? So honestly, when you have to write a surface equation in terms of two variables in parametric form, oh, it makes you enter them each separate. Oh, yeah, enter as comma. Okay, enter your answer as comma separated list of equations. So x equals y equals z equals.
Oh.
Okay. Just know on your test, honestly, you can just let one of them be u, let one of them be v, and then solve for the remaining variable and you're done. All right.
Was this the parametric representation with like two different polyadics?
Yes.
Is there any way you could skip to 11?
Do you want us to skip to 11?
No.
I also don't want to do 10. 10 and 11.
Okay. 10 is evaluating a surface integral not through a vector field. So it's kind of, this is the one where you have to use the square root of 1 plus, or with the funkiness. It's the negative and the negative and the 1. Yeah. So, I might take a minute and do this one.
I forgot.
I think the book used spherical.
Oh, no.
You don't have to use spherical.
Cannot answer.
Oh, whoops, the square got squared. Thank you. So this is just 4 minus r squared. Minus r squared. But it's all under the root. Okay. All right. So let's see how this goes. So we have r cubed. If I multiply this in here, multiply my roots together, I get the square root of 4 minus r squared plus, look at this. Right?
Oh, maybe this multiply together.
Yeah, because root 2 times root 3 is root 6.
It's just root 4 then.
I know! right? It actually kind of becomes like a fun little problem. So you just end up with 2r cubed dr d theta.
This place wishes this was the one.
I know.
That's cool.
It is kind of cool. I love it when things work out nice like that. Yeah, I know. I know. See? You're welcome. Right? Okay. Anyway. All right. 1/2 r to the 4th, 0 to 2 d theta. All right, so we have 8 d theta. So then 8 theta from 0 to 2 pi is just, I get 16 pi for mine. I like that one. Okay, so the main thing is to review the setup. Because the setup gets me. I always forget the setup for surface integrals. So this is where I have to make sure I get this solid in my head. Surface integrals are not my strong point, and I'm the first to admit it. So, all right, so here's how you have to do a surface integral. It is your function, this is your integrand, right? You have to write your integrand in terms of only 2 variables. How do you do that? You're given some surface that you're evaluating over, and you solve this for one of the variables. Whichever one you solve for, then you're integrating with respect to the projection onto the plane with the other 2 variables. So if I solve this for z, I'm projecting this onto the xy plane. If I solve it for x, I'm projecting onto the yz plane, and so forth, right? Okay. So anyway, solve it for z, and then you can rewrite your function in terms of just x's and y's, and then it's your function in terms of x and y times the square root of 1 plus z sub x squared plus z sub y squared. And then you got to clean from there.
So how did you know to solve it for z and not like x?
Because it said z is greater than 0, so I'm, in my head, I'm picturing a hemisphere like that. So it's sitting on the xy plane, coming up this way. So the projection would be onto the xy plane.
Okay.
All right, we did not get to Stokes or divergence. The Stokes one, the one that I picked, is a traditional Stokes going forward, where it really is curl f dot n. So if you want to try this one tonight, you really do have to do curl f, and then n, remember, when you're finding your normal vector, it's just the gradient. So curl f dot n for this guy, and then divergence, it's the triple integral of the divergence. So you're doing the divergence integral over the volume of the bounded surface, the bounded region.
Can you go back to the Stokes?
Yep.
Do you, when you're taking the gradients, do you see
When you're doing the gradient. So when you do the gradient, get everything on one side.
Okay. Yeah.
So you're the gradient.
Right, immediately you say the right thing.
That would be your, we'll call it your, that's your n.
Okay.
Yep.
Thank you.
Yes.